Good morning, everyone. And it's cold because I'm from Canada and I cannot live outside. So this is just acclimatization for me. Um, all right, so I'm Abhishek, and I'll be talking about beyond defect detection. Actually, I'll be talking about what data is and what happens to the data as it goes through the process, how it is collected, and so on and so forth. So that's what the agenda is. Now, I hope, well, by this time you have been to the exhibit floor and you've seen all the really, really cool technology and toys that are on display out there. I mean, it feels like Disneyland. So that's good. And let's just, for a second, take a bird's eye view of the exhibit floor and freeze the frame for a second. And at that time, almost every instrument that's out there on the on the exhibit floor is doing one thing that's common across, no matter whose instruments it is or what the technique is. And what it is doing is collecting a point of data. And in today's presentation, in the next 20 minutes, we'll just take a journey with that data point all the way from where it was collected to something meaningful that we all can use at the end of the day. So I start with mechanization versus automation. There is a subtle difference. We do tend to use the words quite, one as opposed to the other, but they are slightly different. And a really, really good example is when people come to us and say, "Oh, I had collected the data over 30 hours, but then it took me 60 hours to analyze it." It's just the amount of data that was there to work with. So the next part of it is data versus information. The meaning changes on who we are. For an analyst, the image, the C-scan image or the Eddy Current image is the data for them. And it is the information, rather, because they get to see what's inside the part that is under inspection. But as the analysis is done and they have marked indications on it, and it is passed on to the production folks, for them, information is where did it happen, how can I go and tweak my process so that this defect is not created. We'll talk about reporting. This is a really special one because everybody looks for a standard report and then wonders why my report does not look anything like I'm used to looking at. And that's because the standard report is standard, but it's standard for every different technique, every different application, and every different area that you're working in. So we'll look a little bit at, what can we do about it? I mean, one thing is we're going to force everyone to use the same report, which is not going to fly. But then can we do something else to get around it? So we'll take a look at that. And then finally, it's more the essence of the talk rather than a particular slide. We want to design our instrumentation, our automation, our analysis for being obsolescence resistant. A lot of times we're used to seeing things put out there which are basically planned obsolescence. I mean, maybe not that much in the NDT, but yeah, if you talk about your washing machine, it's going to stop working after, as soon as the warranty is wide, yeah, it's going to stop. So what we want to work, at least we want to make an effort going towards is making something that's a little bit resistant to the obsolescence. All right, so let's dive in. If you were in my, or rather Dave's talk yesterday, you would have seen the same slide, but it's a slightly different context to it. 25 years ago, a small company called Google, they started digitizing books. And they didn't stop. And now almost everything is one way or the other published on Google. And Google is a data company, kind of a lot of people like us. We are all data people, right? We all want to look at histograms and so on and so forth just to get started to see what the distribution looks like. So Google has something called the Ngram viewer. You can just Google Ngram viewer and you'll get to it. And if you type a word in the Ngram viewer, it will give you the distribution of the frequency at which it was used over the last however many years. I think it starts somewhere in the 1860s, but we won't go that far. We'll start in 1910. And I went in there and typed in mechanization, and that is the curve I got. So apparently we finished mechanizing everything in 1960 and then stopped, which is, we all know that's not really true. So let's look at automator. Let's not go with the dictionary definition because they kind of talk in circles. So we're going to talk about mechanization as something where mechanical processes are replacing human labor, and that could be for analysis as well. And automation is something where whether it is rules-based or machine learning based, it doesn't matter. It is basically going to automate a bunch of steps for us to get us there. So it was really surprising when I typed in automation, and that's what showed up on the frequency of usage. And we do share a peak around 1960, and we tried to go and look for like what is going on. So a little bit of search, and you realize that in 1960, PLCs became almost very, very common in the industrial landscape. And that's the peak that we are seeing. Now, it's not that people stopped using PLCs after that. It's just that it was ubiquitous. It was so much around everyone that it stopped getting into published papers and stuff. Like, people are talking about other things beyond that. Now, we see another peak happen in 1990s. Any guesses what that is? That is computers, absolutely. That is where the personal computers kind of started invading our homes, our desktops, our offices. And look, Google found it even before, that's probably a decade before Google existed. So we see a peak there. And then obviously I don't have to talk about this peak that is happening right now. And that is the AI ML, I guess to some extent. But more than AI and ML, and that's what I'm going to be talking about, is the and more. And the rate at which we see new technology come into our daily use, a lot of it is because of AI and ML, because we just have so much data right now that we have started inventing way more techniques and ways of interacting with this data. AI and ML is kind of accelerating the process. All right. So, like I said, let's start with that one pixel of data, and depending on who we are, I'm a UT guy, so when somebody says a pixel, I imagine a C-scan pixel, but eddy current X-rays, it is the same idea. So we have a pixel, and we will just go and take a little bit to know it a bit better because we're going on a journey with it. So a pixel is a raw value. It is what your sensor measured. A pixel is the converted value. You go from volts to percent or from microseconds to depth. It has units, microseconds, inches, millimeters, depending on what you're looking at. It will be a data type. Is it a complex pair, if it's eddy current data or not? It's got a data size, 8-bit versus 16-bit, and it's just 16-bit stores more information compared to 8-bit. It's got a size, so it's a physical size. It's not a point of data. It's basically dx over dy, and that's the resolution of your pixel. It has a position in space, x, y, and z. So where it is in space, that is specified for us. And then one step beyond that is it has an orientation. Is it looking that way? Is it looking that way? So we have all that information that can be associated with a pixel. This is a little bit more complex, just a slight bit more complex when you go to voxel or you go to volumetric data. And the only thing that has really changed is all the other stuff is still there, and we have a little DZ in there to look at the voxel size. That's all data description. So we started with the humble pixel, but that's the kind of stuff that one humble pixel is carrying with it. Now, there is instrument type that collected the data, the firmware version, parameters, setup, who the operator was, what the collection date and time, what is the specification you analyzed it against. All that stuff is the data context. It's the context in which this pixel was acquired. So we haven't really left a pixel yet, but we already have so much information that is associated with this one pixel. And of course, as soon as we have that, we start doing analysis. We have indications table, we have statistics, screenshots, and that's the information that, information for the production guys, at least that we end up with. And then it does not really matter how we got that pixel, what technique it was, whether it was X-ray or not. all this information still carries on with the pixel. So let's look at a little bit with data handling. Let's go a little bit beyond the pixel. So whenever we start collecting data, it doesn't matter whether we're using a roller probe, doing it by hand, or a robot. We have to do some inspection planning. So we go and we divide it up into segments, whether it is a raster scan happening on a gantry, or whether it is just a human being going and moving the probe along. Then we collect some data. So we go from one end to the other end, and then come all the way back and do the same thing. And then we collect more data. So this is, I think this particular one probably has a few 100,000 pixels in it. Now, the next step, the very next step that we run into is, yes, we got this data. Now we need to split it, merge it, stitch it, consolidate it, or render it. Very, very different things, depends on what you're inspecting. If you're inspecting small parts, you may want to stitch it. If it's huge parts, like a wing panel, you probably want to split it into different segments so that it can fit on your screen so that you can do your analysis. Now, you bring all this together in a piece of software, and it should not matter. It does matter right now to some extent. It should not matter whose data file that is. But it should be able to, like a piece of software should be able to take it, bring it into it, and merge it all together and get it ready for analysis. So we do some stuff on that front by trying to support multiple file formats to make that process easier. But we are still not there. There are still file formats that are completely locked to vendor-specific versions. Now, if you look at the scan and index offset, because this is just data that is out there in space, it's not really stitched together. So in principle, you can now go in there and type in a bunch of numbers and make them come together. Now, if these scan and index offsets were there with you from the inspection planning stage, even if the files are collected separately, they will come up merged together, ready for analysis. So we skip an entire step of bringing the data together. All right, so let's just look at data organization a little bit more from the perspective of what it is coming off from. It doesn't matter whether it is manual or automated. This is simply a representation of the kind of parts that we might get into, whether it's a storage tank next to my house, well, close enough, or a rocket or an airplane. We will be stitching the data, we'll be merging the data, we'll be splitting it if it is too much, consolidating, and finally, it is rendering of the data that's really important. And rendering, even though it looks like a really nice picture, for most analysts for UT or any of the NDT techniques, analyzing in 3 dimensions is really, really difficult. So what we do instead is do all the analysis, and then we figured out where exactly is our indication on the big part. So it is rendered on the part itself. And it could also be rendered on, I think this is more of a composite part. It could be rendered on a composite part. And while you're doing your analysis, you mark an indication. You already know whether you are in, or you can, if you have sufficient information, to go from part space to airplane space or spacecraft space. So all that information, again, is associated with the pixel and stored in the data file. So the next step here, we're going to look at small parts. Like these were really, really massive, huge parts. So we're going to look at small parts and just see the amount of data that's coming out. So that is an inspection cell, an automated inspection cell. They are inspecting clips that kind of hold the fuselage together for the aircraft. Brad had just gone and scanned the QR codes of the cells where the parts were. And it flips around. The robot has 3 tools to choose from. It's going to pick one of them up. It's going to go and grip a part. And these are really small parts. But as you can see, even the small parts have 4 faces, 4 flat faces, and a couple of radii. So that's about 5 scans that the robot is going to do. And it has to grip it from different angles. It's going to go and grip it. There's the radius probe. There's a flat probe here. And it's going to collect the data. That is really great because it has gone from, while we watch this video, from picking up the part, loading the correct set of file, validating whether it is qualified or calibrated or not, and collecting the data. And by the way, the gripper doesn't always pick up the part the right way. So while the video was going on, the robot actually went in and corrected its path to make sure that any angles are taken out of it. And yet we do 30 parts an hour. And if each of those parts have 5 scans, that is 150 scans. If you have one operator analyzing 150 data files, that's 0.4 minutes. That's 24 seconds, a data file. So that we can see is starting to get us into trouble. But if we do something slightly different, which is we decide how the parts are going to merge together, before the inspection is done, all these 5 files have been merged into a single data file. So now I think it's more like 2 minutes of analysis time per data file. And we don't stop there. We go and say, OK, you use a QR code to tell the robot what the part was. So why don't you just go to the analysis software and scan the QR code, and we will load the data file from wherever it is, or the most recent copy of that data file. And a lot of times you'll see that this part of the work is done very, very unique to a system, because every QR code is different and so on and so forth. So we tried to come up with a mechanism where as long as certain rules are followed, and as long as you are able to define the format of the QR code, it does not matter whose QR code is, a canned off-the-shelf software will open the data file. All right, so let's go to the next one. And this is more to do with information handling. So this is the stitched part together. We went and marked like 4 indications or 3 indications on it. Great, and let's see data explode at this point. When we started making this indications table, you only see like 7 or 8 columns out here, and those are mostly the stats. But in reality, this particular indication, or every indication in there, has at least 50 parameters associated with it. Some of them are statistical parameters, some of them are information around the pixel, some of them are information about where the pixel is, and some of it is operator or rather analyst input, like how they sentence it and so on and so forth. And when we did that, I was very happy. I'm like, yay, Eureka, we have done it. And we went to one of our, at that particular time, it was being qualified for a heat exchanger system, for heat exchanger tubing. And the level 3 goes, well, that is really awesome. How do I get it into Excel now? I'm like, why do you want it in Excel? And she explained that a lot of times the first level of analysis is actually based on empirical equations collected over data that they have collected in the past on these tubes. And this happens in most places, in most production environments. So fair enough, Excel does make sense here, and you should use whatever makes sense to be used here. But the problem is, as soon as the data goes into Excel and you start adding information there, our connecting chain with that pixel is now broken, unless somebody goes and manually types that information in. So we said, OK, what can we do? So we said, OK, we'll give you some Excel-like capabilities inside the software. And would 5 user-defined columns would be enough for it? And she goes, yeah, that's perfect. 3 days later, she's back, and she goes, can I have 5 more? So we said, sure, 5 more. And then she's back 3 days later. She said, I'm so sorry, but I need 5 more user-defined columns. So I said, why don't we do 50, and then when you run out of them, we can add more. It's not that it's costing me anything to add columns, but we just don't want to let it go uncontrolled. She hasn't come back yet in 3 years, but I'm pretty sure at some point someone will be back. So anyway, so now we are doing Excel-like calculations, and by the time we reach Excel, we will reach Excel eventually. In the next slide, you'll see that. But by the time we reach Excel, we have done a lot of the work which is already correlated and connected to each other. So let's just take a quick journey, 5 more minutes, on our reporting part of it. So we have the raw data. Great, it's very structured. It's in pixels, it's in a grid. Now we take the raw data and do analysis on it, which is also great. And that's where things start changing very, very rapidly for us. You get Excel as a formatted report. You can do share reports with PDFs and PowerPoints, but there is a problem, and it might not look obvious, but that's all unstructured data. And we're like, what are you talking about? Excel and PDF reports are very structured. There's a difference between structured and organized. They are very organized reports. For a human mind, they're very easily able to go and read it. But for a computer to go and crawl that data, it's really hard. I mean, you can go and give Excel cell names and so on and so forth, but see, you're bringing in structure at that point of time. The other way, of course, is just put it in a database. Like Andy has been doing it forever, or DICOM rather. You can create a database and off you go. There's a problem there. If you have not defined a field in your database and you need to add it 5 years down the line, it becomes really, really difficult to deal with those and interact with those. So it's not that databases are bad, it's just that they are a little inflexible if you haven't thought of what's going to happen in, well, it's 2024, what's going to happen in 2030. So let's see what we can do about it. So what we started doing was we took our report and put it in a JSON format. You can put it in XML or wherever, it doesn't really matter. It's semi-structured data out there. There's some structure to it, but you can add more structure to it. It doesn't really matter. And it's human readable. Like you can still go in there and you can read the JSON, and you can write scripts to crawl it, and that's awesome. So it contains all the useful metadata, everything about the scan, like all the things we talked about with our little pixel up front, all that is in this JSON file. It contains no raw data because we've already gone past that step of dealing with the raw data. Now, the JSON report itself, it's semi-structured, human-readable. It can be accessed programmatically, and you can do stuff like analytics on the data. Go find me probe with the serial number and show me how the TVG curve changed over the last 10 years, or not, well, too much, last 10 months, let's say. You can do production and process tuning. If you start seeing a heat map on a particular part in a given location starting to add up, you can just say, hey, guys, there's something going on out there. You can do life prediction of transducers. I think I gave that example. And then you can create, let's go back to it, the custom report. So you have the reports, but they are not coming directly from analysis. They are going to the JSON and then being parsed out of there, which basically means you can have a lot of scripts that you can write for a lot of different kinds of reports. And that is the whole idea for the reporting in different formats, whatever the standard is. You can have our default report that sort of kind of looks like that, where you can add or remove any parameter that you want in it. It could look like that. That's a customer's report, which I have cleaned up a little bit so that you can't identify it, but that's a report that they have been using for ages, and they cannot move away from there. That's their standard report. And it was very little work for us to go from the JSON into a report that looks like that. It's the indications table coming out. There is that report, which our friends in the corrosion market are pretty familiar with. You want the report to go in as a C-scan inside of Excel. Sure enough, that can happen. And here's the best part of it. This is the JSON report. You can read most of the stuff that are there. And JSON, by the way, can contain images as well. So if you have an image, a PNG, you can just stuff it in the JSON, and it will be good enough for it to be called back out. So that's the report from which, that's the base report from which everything is coming out. And the really nice thing in here is, everybody's talking about agentic AI and large language models. Well, this kind of organization of data can be very, very easily crawled by agentic AI and to go and do stuff on it. And if that does not pan out for whatever reasons, a lot of us can write tiny little scripts to go and parse information out of these JSON files which are stored somewhere, including in a database. So that's it. That's my presentation. Thank you for your patience.